Hi, in today's video we are going to be discussing Newton's laws, and we are going to be discussing how they relate to various different scenarios. So at first glance this might seem very daunting. I've got all sorts of different equations in front of you. Just rest assured it looks worse than it is. For us to get started here, we're going to want to look over Newton's three laws. A body continues at rest or in uniform motion in a straight line unless acted upon by some outside force. The second law, the acceleration of a body is inversely proportional to its mass, directly proportional to the force, and in the same direction as the force. And finally, the third law, to every action there is an equal and opposite reaction. And to get us started, we're going to do some warm-up problems. And for our first warm-up problem, we are going to look at the gravity of, compared with gravity at Earth's surface versus how much weaker gravity is at a distance of 10 Earth radii from Earth's center or 20 Earth radii. For this, we are going to deal with G1 over D2 equals G2. This indicates this would be gravity at the Earth's surface or gravity at some distance and the new gravity at that new distance. So for this, we're just going to use 1 as a placeholder. It's equal to 1G or 1 Earth's gravity. And by dividing by a radius, or a distance in this case, we're going to be able to determine what the value of G2 would be. So for example, this first one here, we would set it up as 1 over 10 squared. So your answer for G2 here would be equal to 1 over 10 squared or 1 over 100. So at 10 Earth radii from Earth's center, we would have a value of 1/100th of the gravity that we would see at the Earth's surface. You try out this next one for 20 Earth radii. For the next problem down, we are asked to compare the force of lunar gravity on the surface of the moon with the force of gravity at the surface. For this, you will notice that we have a value given to us for Earth's gravity here. The acceleration due to gravity is 9.8 meters per second squared on the Earth's surface. I will tell you that the gravity on the moon is 1/6 the gravity, the acceleration due to gravity on the Earth's surface. So you do the math there and find out what 1/6 of 9.8 meters per second squared would be, and that'll be your answer for number 2. For number 3, it says, if a small lead ball falls from a high tower on Earth, what will its velocity be after 2 seconds, and also after 4 seconds? For this one, you're going to, once again, need to use the 9.8 meters per second squared. You're going to multiply that by the time interval, in this case 2 seconds, and then you'll get an answer for how many meters per second it will be moving. So there should be 2 problems here, one for 9.8 times 2. The second one is 9.8 times 4. And they'll give you 2 values, and they should be in meters per second. All right, so for the next set of problems, we're actually going to have to rewrite the formula from the front page. For this type of problem, we are asked to calculate the weight in newtons of a 100 kilogram, which is 220 pounds. We're going to use the kilogram value, though. A 100 kilogram alien on the surface of each of the following planets. First, I have here Mercury. Second, I have Mars. Then I have Jupiter. And for each of these, you're going to be measuring using the equation that's found right here, force due to gravity, weight. This is for any gravitational body for which we have the gravitational constant, big G, which is always 6.67 times 10 to the negative 11th right here, times big M. Big M is the mass of the planet, or the larger of the two objects in any case. In this case, it's a planet. And then little m, which is the mass of the alien, which in this case is 100 kilograms. And we're going to divide the entire thing by the radius of the planet squared. Notice the value here is negative, which indicates that the force that we're going to be providing is moving down. That's what the negative value means, down. Don't forget the negative sign. So you'll take 6.67 times the mass of the planet times 100 divided by the radius that's provided of the planet squared. That is going to be the equation we are using right here. And here's the radius of the planet. It's in meters. Here's the mass of the planet, Mercury, in kilograms. And you have 100 kilograms as the weight of your, or I should say the mass of your alien. And that's all the information you should need. The same thing will be done for the Mars and Jupiter. Be careful here for all of these. You need to have your equations set up using meters, seconds, and kilograms in all cases. Notice here we've got kilometers. So you're going to need to convert this number first from kilometers to meters. Remember, there are 1,000 meters for every 1 kilometer. Once you have it converted for that, you're going to need to then plug it into the equation. The next equation that we're going to be using, we're going to have to once again rewrite the formula for these next sets of questions. We're going to be using the circular velocity equation, which on page 1, circular velocity is this equation right here. V sub c is the square root of big G, which is the gravitational constant again, times big M, the mass of the planet or body that we're orbiting, over R, which is, once again, the radius of our orbit this time from the center of gravity. So in the case of a planet, that would be the center of the planet. In the case of a sun, that would be the center of the sun. Or it's actually the barycenter. The barycenter is the centralized location between two bodies where gravity is equal. Now, without being too confusing, the numbers I'm going to give you for radius are just that, the numbers that you're going to get for radius. So plug it in. Common mistake, people forget to use the square root function here. My suggestion is do all the math inside first, get it one number, and then take the square root of it. So let's take a look at that for circular velocity equations, number 7. Okay, so you are asked to find out what the circular velocity of the Hubble Space Telescope is. It lies at a distance of 569 kilometers above the Earth's surface. And keep in mind, the Earth's radius is also 6,378 kilometers. You need to do some addition. Don't just go with one of these two numbers. You need the full distance from the Earth's center. Once you have this value, we are going to get the circular velocity. It's asked also for you to get the orbital period of this particular satellite. For orbital period, we can actually go back to our equation for Newton's derivation of Kepler's third law, or right here. Okay, so we can plug in our value then. 4 times pi squared over the big G, which is, once again, the gravitational constant here, times the mass of a planetary body, which is the Earth in this case, which I've given you the Earth's mass right here, in kilograms, times the radius cubed in this case. Keep in mind, for the radius of this, it's the full radius, once again, of both the distance above the Earth's surface as well as the Earth's radius added together. That's what we would use for this part. Number 8, we have once again the circular velocity equation and then the orbital period using the Kepler's derivation of Newton's third law. Or I should say Newton's variation of Kepler's third law. Once again, another circular velocity equation with number 9. And once again, the orbital period. Same calculations. Escape velocity. For the escape velocity equation, we're going to be using this one right here. Okay, V sub E for escape. And we've got, it's the square root of 2 times the gravitational constant times the mass of the planetary object times the radius. Notice that this is twice the value underneath the square root that you would get from the circular velocity equation. Interesting. So this is the escape velocity necessary to escape the gravity of a planet if you wanted to go to some other planet or out of the solar system, for example. So for that one, we have escape velocity equation up top here. We plug in our value for our mass. Make sure that, for the radius. Make sure that it's in meters like this one. Notice that this one's in kilometers again. Once again, we provide you with the mass of the planet, and you're plugging that in for these 3. Okay, and that uses, once again, the V sub E equation. Finally, at least is the bonus opportunity. For this one, it says use the Newton's derivation of Kepler's third law to solve the following problem. So solve for the mass of a planet, given that the orbital period is of a small satellite at a distance of 40,000 kilometers. Be careful, kilometers instead of meters. And is equivalent to 97 hours is the period. Okay, so 97 hours. Remember, needs to be in meters, seconds, and kilograms. So you're going to need to first convert 97 hours into seconds. You're then going to need to convert 40,000 kilometers into meters. And then you're going to need to move this equation around first to solve this equation for R. And then once you've got, to solve for mass, big M. So you're going to solve for big M here first, move this equation around, and then plug everything in. Okay, I need to see work for this. And if you can provide me the work, I will provide you a bonus point for this activity. So this activity will be worth probably a total of 20 points. Okay, and in fact, you know what? I'll give you two points for the bonus. All right, so if you have questions, please come see me. Otherwise, good luck.